I'm the next speaker also. One of my colleagues, Evan, put in the thing for the proposal for the talk, so his name is on the schedule. But we're going to split it into three little lightning talks instead. So I'm Carl Pearson at Sandia. This is Cedric Chevalier from CEA and Evan from Tennessee Tech. And we're going to talk a little bit about Kokkos Comm. So this is I'm going to talk a little bit about sort of the overall vision for the effort, and I'll let Cedric and Evan talk about what they're interested in talking about, since they're some of our core contributors. So I kind of bolded their names there on the bottom, but we've got a crew of kind of interested folks. But basically, it kind of runs the gamut from some relatively, I don't know if straightforward is the right word, but maybe less ambitious to more ambitious kinds of aspects. So initially, we're kind of thinking about lots of people use Kokkos for on-node stuff, and then they end up writing some kind of MPI interop to do their distributed memory. So I think we're kind of interested in trying to formalize a way to do that and remove that minor burden from people so they can get on with their lives. That's sort of the most near-term stuff. We've heard about various challenges related to Kokkos and MPI even earlier today. Some of the STID execution. There was some talk about communicators and communicator initialization and things like that. And so, and more ambitious, we're kind of thinking about better interfaces for MPI using modern C++ language features and things like that. So various folks on here are interested in different aspects of this sort of overall effort. But just to kind of make this a little bit more concrete, if this is not exactly your wheelhouse, so I just sort of cooked up this example about a little function that sends a view, a templated view type somewhere using MPI. And it also, has some kind of synchronization semantics with a Kokkos execution space. And so there's a couple of things you're going to have to grapple with, or at least consider when you're writing a function like this. And so I'm sure many people in this room have done this. But if you haven't, the first question you're going to have to ask yourself is, what do I do if the data in my view is not contiguous? And there's a couple different things that MPI sort of naturally provides. Data types, packing, you could pack it yourself, some things like that. So what the right thing to do there is not always obvious. Even if your view is contiguous, you're probably going to end up having to describe the layout of that view to MPI at some type in some way, which is kind of a little bit clumsy. We're going to have to make sure we synchronize with Kokkos, right? Because Kokkos might be doing something asynchronously, and the MPI functions will expect that work to be done before they take over your data. We might throw some profiling regions in there and then actually use MPI. And then there's kind of a subtle problem with this code too, which is actually if this view that's being passed in here, that when this function returns, if this view that's being passed in here, the reference count goes away to 0, then MPI is going to probably quit on you and bring your whole application down along with it. And so that's something that you have to keep track of the lifetime of your views with respect to what MPI is expecting. So kind of the way we're approaching this, at least at the beginning, is we're going to provide two kinds of APIs. We have a simple one, which is basically just MPI, except it takes Kokkos views instead of pointers. So this is really just sort of search and replace ergonomics. It doesn't actually help you solve the problem, any of the more complicated synchronization or lifetime problems. But it still will, automatically add Kokkos Tools integration and things like that. Then we're going to have a safer API, which has some runtime overhead that does handle some of these things with respect to various memory spaces and making sure the view lifetimes are long enough and things like that. And it'll also do everything the simple API does. And so what I'm trying to show with the plot here is basically just on a CPU and a GPU node. The absolute values of the numbers are not that important. But what's important is that we're aware that people are sensitive to latency regressions in their communication, and that's something we're actively trying to keep track of as we go through this effort. The second piece that's a little bit interesting, I think, is working around platform-specific problems with MPI. So I think if you've ever worked on MPI across different computers, you discovered that things that work well on one system don't work well on another system. And we kind of see this place as a way to, where it fits within the API, work around some of those problems. So whether that's putting in a substitute implementation for a collective, handling non-contiguous data in a certain way, right? There's all kinds of little warts that pop up in different MPI systems and configurations that we could defend against a little bit here. So on the code on the left here is ping-ponging some, just a relatively small number of non-contiguous bytes between two processes. And the kind of interesting thing is the MPI bar is if you describe this non-contiguous region with a data type and just call like MPI send and receive directly. The middle bar is if you use an MPI data type and then pack it with MPI pack, and that's actually faster in this particular implementation, which I can see no reason why that should ever be the case. And then in the Kokkos Comm one, we just internally allocate some scratch view and do deep copy, and you can see it's like 200 times faster than what MPI is doing, right? So like, this is not going to be the case on every system, but this is the kind of thing that's relatively easy for us to do for you. So really briefly, before Cedric takes over, beyond this kind of basic stuff, we're kind of interested in seeing if we can develop a core API that is smaller than MPI's API, but is still sufficient for people's use. And if you're willing to restrict yourself to something like that, then we could use vendor-accelerated libraries like Nickel or Rockel or whatever anyone else cooks up. The idea being sort of analogous to, if you're willing to restrict yourself to using Kokkos views and writing parallel for, parallel reduce, et cetera, you can take advantage of Kokkos on various systems. And even beyond that, there's people who are interested in using this as a vehicle for research. So modern C++ language features, device-initiated communications, new collective communication strategies, and some integration with Kokkos tools around choosing dynamically how to do communication in applications. So this provides an attachment point for all of this kind of work. So we're part of the Kokkos org. We got a channel on the Slack, and we've got some CI testing stood up using Sandia and GitHub Actions resources for a variety of backends. Recently, Nicole, who's not here, checked that everything was working on the HIP backend, so that's great too. So that's all. That's my brief little spiel, and I'll hand it over to Cedric for him to talk about what he wants to talk about.
Okay. Okay, so I will talk a little bit about what has been going on during this 1 year of this project. So I think we are the youngest project in the Kokkos ecosystem, the Kokkos repository. And I will focus on the challenges we have faced. So some were expected, how to deal with the data, how to ensure the code quality, but still you have to set up the CI. We need a network to test properly what we are doing. So this is a little bit more complicated than we wish, but we are now in a good shape, at least to try to use GPU and MPI in our CI. We want also to explore the new features of the communication layer we are using. So for example, in MPI, we can use session to avoid some pointer checking, for example, or we want to be able to tune some algorithm to have better performance. And we were thinking about using this new communication library like Nickel, but Nickel has a very small subset of function, like 7, and there is no all-to-all. So I'm not sure it's really okay for HPC application to provide a communication layer without all-to-all. So we have to figure out a small API, but enough for our user. And we had also some question about how to deal with in-kernel initiated communication. So it might be possible to use MPI call from an OpenMP region, but it does not have any sense to do this from a CUDA kernel. So we choose to not allow this kind of patterns. And the big challenge is how to deal with asynchronicity. So it's mostly, the slide I think is a mirror of the talk of this morning by Michael. And we will look at stewed execution to see how it can help to deal with asynchronicity from both the communication layer and the the device and the accelerator. So it's a small conclusion. It's just that there is finally a lot of challenges, and if you have ideas or if you have needs, please tell us, and it will help us to provide something that is usable for the community. And now I will let Evan talk about more scientific things.
Hello, my name is Evan Suggs. I'm from Tennessee Tech University. I did this work, and I have to give as much credit as possible to Nicole, who did most of this work, on persistent Kokkos Comm, a version of Kokkos Comm using persistent communication. So, there are several challenges we wanted to address here, and in addition to, the challenges we want to address with Kokkos Comm, which are, you have to handle non-contiguous data across Kokkos and MPI. You have a lot of platform-specific, work going on for, handling data. How, Intel, AMD, NVIDIA GPUs, they all handle data differently, and how heterogeneous architectures complicate data exchange, when you're on a big system. So Kokkos Comm, as talked about in Cedric and Carl's talk, is aiming for all varieties of communication. And we wanted to target persistent communication especially, but we also handle partition communication. So persistent communication initializes communication once, benefiting internode communication by reducing overhead during communication. And we implemented this in Kokkos and MPI via a channel object that handles requests for the communications for both persistent and single partitioned point-to-point. So it has both functions. And this is a pretty simple send, receive init, a send init, receive init, a start that actually begins all of these functions, and a wait interface. How much time do I have? Oh, good. So the real meat of this is we implemented this. We wanted to enable the fastest path for any data to move without changing the program, and we ran tests on both Sandia's Weaver system, which has Tesla V100s, and Lawrence Livermore's Tioga system, which is AMD MI250Xs. So in this graph, we did a very basic send-receive benchmark, and we actually got a lot better time on Tioga for our persistent and our partition communication. And this is just an average over 100 iterations for this work. But we also did, in addition to this, we did a Heat 3D and some OSU benchmarks. So here's the Heat 3D. And this is, sort of less convincing. The standard MPI performed maybe a little better than, the MPI data type stuff. But overall, they performed pretty similarly, except in the CUDA example, where the MPI data type performed much worse. Similar story here, where they performed almost identically in all situations. You can see that the Kokkos Comm performed maybe a little better, but without going really in, they performed pretty similar, which is good. We weren't aiming to reinvent the wheel here, but no, here's a more interesting one, where the real time, these both used deep copy and non-contiguous, for these. and, they had wildly different ones. So the MPI data type performed, sorry. They performed wildly differently. So conclusions, we were able to implement a channel object, that performed half duplex, persistent, and single partition point-to-point communication in Kokkos Spawn. We're hoping to expand upon that. Persistent and partition types perform better than standard. We, as talked about earlier, we added explicit HIP support. Nicole ran that to complement existing CUDA support. Kokkos Comm has been fully instrumented for Kokkos Tools, as mentioned earlier. And I wanted to talk more about future work. We want to enhance Kokkos type support, include MD span, add new communication space backends such as Nickel. And more related to the partitioned work, we want to add stream-triggered communication. We want to add libfabric. And we're hoping to do the stream triggering in a pretty similar fashion to here, where we could invent a Kokkos stream object or queue to handle everything together. And we have this roadmap here for what we're hoping to do. So we have MPI persistent and partition communication on here. And we're hoping to add RMA and stream triggering. I have added stream triggering to Kibana. So that's working, but that's not using Kokkos Comm. And we're hoping to port some of that down to Kokkos Comm in the future, and then add libfabric. Well, that's the end of my talk. Here's my acknowledgements.
Thank you. Questions, anybody?
Thanks, nice talk. Just wondering if you could say a word about integration with Kokkos remote spaces.
Yeah, so great question. Yeah, so there's this complementary project, I would say, called Kokkos Remote Spaces, which takes more of a like SHMEM style approach, where there's a view, something that looks like a Kokkos view, but the data is distributed across different nodes, and you can sort of transparently access the data of your neighbor. So is Jan in the room? So this is. He left. Okay, so I can say whatever I want. So this is I think this is mostly Jan's brainchild. So I'll try to speak for him. So I think this is largely complementary to that in the sense that like a message passing kind of communication style is complementary to a SHMEM style. My expectation would be that maybe in certain kinds of highly structured communication patterns, maybe Kokkos Remote Spaces provides a more natural, easy to understand, high performance way to do some things, and maybe in something that's a little less structured, going to message passing might be a better way to do it. But we are interested in some of the same topics. It's possible that we'll collaborate on some of these things, especially maybe more advanced C++ language features. That's an area of interest of Jan's as well. So that's Jan Siesko. I think if any of that sounds interesting to you, I suggest you track him down, after the session if he doesn't come back and ask him about it.
He left for the day.
Okay.
Like that,
well,
so.
You can find him on Slack. I guess I'm also supposed to moderate for the next session, so maybe I should have our next speaker come up, and if I can quickly answer. Sorry, trying to juggle too many balls here. So, if maybe I can answer one more question while you're getting set up. Mm-hmm. You might want to use that if you.
Does the Kokkos kernel place any requirement on MPI init threads? The value that you need to give to MPI when you initialize it? So you can give MPI funneled.
Right.
Yeah. Does it pass any requirement on that?
Yeah, so this is a good question, and so part of that's going to depend on, if you're using the Kokkos threads backend, we may require that MPI be initialized in like a compatible way. That has performance implications potentially. I think the other thing that's a little bit of a question mark in our mind still is to what extent do we want to take ownership of the initialization of these communication packages? I know that's been sort of an ongoing pain point of handling initialization in Kokkos. But yeah, I mean, this is a good question, and it's something we could at least maybe protect people from choosing something incompatible at the very least.
Yeah, and if we move to session, on session, you can activate depending on the session. If we manage to move to MPI session, we can change the behavior depending on the session. So it's something we have to go, but currently we are more defensive, and it's the user to initialize MPI.